Hello, my name is Robin Mitchell and welcome to EFM Electronics for Makers. In today's episode we're going to be looking at the MitchElectronics AC DC 5V regulator. So what is the purpose of the MitchElectronics AC DC regulator? Well, it does exactly what it says on the tin. It converts an AC source or an AC power source to a 5V DC source that can be used to power other projects, kits and things you make. But there is something about this kit that we should probably clear before you carry on. This kit is an AC DC regulator, but it's not designed for mains use. You can't put 230 volts into this thing and expect to get 5 volts out. This has a maximum input voltage of around plus or minus 16 volts. So do keep that in mind. It's only designed to rectify small AC sources. And this is mainly for demonstration use, but it does have some small practical applications. For instance, while it is an AC DC converter, it can convert a DC into a DC. And what we mean by this is that you can plug in a DC power supply in any orientation and it will still function because of the rectifier. And you could actually use this in a project to make a battery system where it doesn't matter which way you connect the battery in, the device still operates. But short of that, that's really all you can do with this kit, unless you do have a small AC source, in which case you can convert it to a 5V source, and that could be very, very useful. So how does this kit work? So here we have the full AC-DC regulator circuit, and it consists of two main sub-circuits. We have a rectifier and a regulator. So the first step in this circuit is to take a AC waveform and turn it into a DC waveform. Now that doesn't mean that the DC waveform is going to be flat and straight like a battery, but it means it won't have a negative component. So what does this mean? Well, for example, your AC would look something like this, where you've got a positive component and a negative component, where this graph represents voltage and time. And a DC waveform could be something like this. Now, yes, the voltage is constantly changing, however, there is no negative components, it's all positive. And so that is the role of the rectifier. So how does the rectifier work? Well, let's start by rubbing this off and having a look at the rectifier circuit. So here we have our AC rectifier circuit, and we have our two inputs, AC1, AC2. This is the pair of wires that comes from our AC source. And we also have the Vout signal, which is our DC output, and the 0 volts output, which is also the DC output. You've got a ground and a positive output. So this is how it works. So let's start by assuming that AC1 is the positive part and AC2 is the negative part. So for example, if you took an AC source like this and you have two leads coming out, this would be AC1, this would be AC2. So if AC1 is positive with respect to AC2, so let's say you've got something like this, right? That would be with respect to AC2, and this would be the voltage of AC1. So during this positive part, D3 becomes forward biased because the back part of this is bigger than that part, and so the current can flow through, so the output becomes positive. And if we find my red pen, this is what the current path would look like, conventional current path would look like. And so that's positive. At the same time, AC2 is the negative part. So basically that means if this is negative, then D4 becomes forward biased because this bit here is smaller than that bit, and so the current returns through D4 and then into AC2, and that's one half of the waveform being rectified. So this would be this half. But what about this half where AC1 becomes negative and AC2 becomes positive? Well, if we just quickly get rid of these. So now that we've seen what happens when AC1 is positive and AC2 is negative, what happens when that flips? Well, the first thing you see is that D5 becomes forward biased, and so the current can flow through AC2, goes into AC2, around D5, into the output, so it remains positive, and the return current comes through here, and it can't go through D4 because that would be reverse biased. However, D2 is forward biased because the voltage here is smaller than the voltage here. So it's smaller at the cathode and the anode, and that's what makes a diode forward biased. And so therefore the current can return through D2 like that into AC1, and that graph there on the output ends up looking like this. And so now we've gotten rid of the negative component of the AC waveform, and it's all in the DC. And that is the purpose of the rectifier stage. Now, of course, a voltage that looks like this isn't really practical. We can't connect that to microcontrollers. For one, it's not regulated. For two, it's going all over the place. So we need to convert this wobbly line into a straight line like that. So to do this, we use two main parts of this regulator, which is a capacitor, a storage circuit, and then a regulator. So if I find this and wipe that off. So the first part of this regulator circuit is a smoothing circuit, and the objective of this circuit is to try and remove as much of the ripple as it can before it gets regulated. So let's say, for example, we've got this 470 microfarad capacitor here. The job of this is to convert this into that. Now, while this is still not practical for microcontrollers and other sensitive circuits, it is far better than what we had before, where we had these areas of no voltage. So the job of the 470 microfarad capacitor in this circuit is to act as a storage bank, which puts out voltage when the input from the AC rectifier is at the minimum parts. But again, this needs to be converted into a straight line, and this is where the regulator comes in. The 7805 regulator is a voltage regulator that takes in a big voltage on its input and turns it into a fixed voltage on the output. Now, the 7805 produces 5 volts on the output, and it can only produce 5 volts as long as the input is greater than or equal to around 7 volts. Now, I don't know the exact number, but it's around here. So as long as our ripple coming from the storage capacitor, this little wobbly thing, as long as that is above 7 volts, then the output of the 7805 will always be a steady 5 volts. And that is how the AC-DC regulator circuit works. Now we'll just quickly look at the last few components that make up the circuit and what their roles are. So the first two components you'll see that haven't been mentioned are C1 and C4, and these are called decoupling capacitors. And the purpose of these capacitors is to remove noise that could inadvertently upset the circuit. Now when it comes to noise, a good example of what generates noise and is quite problematic for power circuits are microcontrollers, Arduinos, microBics, etc. Now, these devices are great, they can run code and perform all these different tasks, but they also switch really fast, and this switching can basically find its way onto the power line. So for example, what we would like is a steady 5 volt power rail like that. However, when you have microcontrollers attached to this 5 volt rail and you looked at it on an oscilloscope without any decoupling capacitors, you would most definitely see things like this. Now, while that may not be a problem for most circuits, the truth is that those little wobbles can actually affect how microcontrollers work. Sometimes it can cause them to stall, it can make them you can confuse them, they can do mathematics wrong, they'll get bits flipped, it can affect analog circuits. It's an absolute nightmare, and especially for products on the market, and they have to get rid of this. So the purpose of C1 and C4 is to help smooth these out by using tiny capacitors that can react very quickly to sudden changes. So the adding decoupling capacitors like C1 and C4 essentially helps to reduce that noise, so you've got a more stable 5 volt rail. And the last two components that we're going to look at are D1 and D6 and their purpose. If we take a look at the 7805, you'll see that on our circuit we've got a diode going this way on the input and the output, and we've also got a diode going like this. Now the purpose of, oh actually let's give them names, D1 and this is D6. Now the purpose of D6 is quite interesting. Essentially it stops the output going negative. Now the 7805 isn't really a sensitive chip, but like most silicon devices, it does need some level of protection to make sure it doesn't get damaged in the silly situations. Let's say, for example, somehow the output became a very large negative voltage because of some poorly designed circuit that had an inductor and had a large back EMF. So the purpose of D6 is to make sure that the output can never go negative relative to the 7805. So if, for example, on normal conditions, this would be 5 volts here, then D6 would be reverse biased and therefore won't conduct any electricity. However, if the output, let's say, went to -15 for some weird reason that we couldn't control, what happens is that D6 actually becomes forward biased and therefore conducts the majority of the current away from the 7805, so that the 7805 is not damaged by this negative voltage. And you'll see we've got another diode, D1, and the purpose of this one is to make sure that the output is always less or equal to the input. Now this may seem strange, but in certain situations, let's say we had a very large voltage swing on the output, let's say it jumped to 15 volts, well, the D6 is not going to protect it. However, D1 will, because if the output became say 16 volts and the input was 7 volts, well, the input's less than the output and that would damage the chip. But D1 would become forward biased because 16 is bigger than 7, and so current would flow around the 7805 onto the input and raise the input voltage to approximately the output voltage, and therefore protects the 7805 from sudden increases on the output voltage. And those are the two main safety features on the AC/DC regulator kit. Well, that's all we have time for today in this episode. Thank you for watching and see you next time.